Hi, welcome to my YouTube channel. In this video you will learn basics of digital electronics. And by watching full series of videos, you will understand more about digital electronics. In today's advanced age, many of the electronics devices we are using every day are digital devices and some are analog. Digital devices work on digital signals. These signals are in the form of digits, which are 0 or 1. Examples of digital devices are computer, laptop, mobile phone, camera and storage devices, etc. And analog devices work on analog signals. Analog signals are time-varying quantity. Examples of analog devices are amplifier, old telephone line and old television. Let's understand analog and digital signals well. Analog signals. Analog signals are signals whose value changes over time, and most of the things in the universe that are measured are in the form of analog signals. Temperature, time, pressure, and sound are the examples of analog signals. Digital signals. Digital signals are signals that have only two positions, high or low. Where high is equal to 1, and low is equal to 0. If the voltage are 2 to 5 volts, it means high or 1, and if voltage are 0 to 0.8 volt, it means low or 0. Because the position of signals in a digital system is either high or low means 1 or 0, that's why the digital signals are called binary signals also. Analog devices versus digital devices. All measuring instruments that express their measured value with the help of a needle or pointer through a calibrated scale for a rating such as voltmeter, ampere meter, frequency meter, temperature meter, are all analog measuring instruments because the pointers move constantly with changes in the amplitude of the measured values. In contrast, all measuring instruments that do not consist of pointers and scales and display their measured value in the form of individual digits or discrete digits are called digital devices. Binary codes or digital codes. Binary code, code used in digital computers, based on a binary number system in which there are only two possible states, off and on, usually symbolized by 0 and 1. So, the components or devices that process through digital codes are called digital components. And study of such components is called digital electronics. To learn more about digital electronics, please subscribe my YouTube channel and press bell icon to get notification of new videos. Thanks for watching. Goodbye.
So this video is for those of you who want to get an introduction into electronics. So one of the first components that we're going to talk about is resistors, because typically you'll find them in almost every electronic circuit. Resistors are designed to limit the amount of current flowing in the circuit. And you could calculate the amount of current flowing in a circuit using Ohm's law. V equals IR. V stands for voltage, measured in volts. I represents the current measured in amps. R is the resistance measured in ohms. The current flowing through a resistor is the voltage across the resistor divided by the resistance itself. So let's say we have a battery attached to a resistor. The long side is the positive terminal of the battery. The short side is the negative terminal of the battery. And let's use a 12-volt battery. Conventional current is going to flow from the positive terminal of the battery through the resistor back to the negative terminal of the battery. Conventional current flows from a high potential to a low potential, but in actuality, electrons flow in the other direction, from the negative terminal to the positive terminal. So that's really what's happening in this circuit. Electrons are the charge carriers. They're the ones that are moving through the metallic conductor. But now let's make a table that shows the relationship between resistance and current. So let's say the resistance is 3 ohms. Using this formula, if we take 12 volts divided by 3 ohms, we're going to get a current of 4 amps. Now, what if we increase the resistance? Let's say from 3 ohms to 6 ohms. What's going to be the current? Well, using the same formula, if we divide 12 volts by 6 ohms, we're going to get 2 amps. And so note the relationship between resistance and current. If we increase the resistance in a circuit, the current decreases. And so we could use this device to control the amount of current that is flowing in a circuit. If you want to increase the current, you can decrease the resistance. If you wish to decrease the current, increase the resistance. Now, sometimes you may need to decide what resistor to use in a circuit. And one important consideration that you need to take into account is the power rating of a resistor. So let's say we have a battery attached to a resistor. And let's say this is a 100 ohm resistor and the power rating is 1/2 watts. Power is equal to voltage times current. It's also equal to the square of the current times the resistance, and it's equal to V squared over R. So you could use any one of those three formulas to calculate power. Now, this is important because if you apply too much power to a resistor or too much voltage, the resistor can burn up, it can get hot, and that could create a lot of problems. So you need to control how much power you deliver to a resistor, because it can only dissipate so much without damaging itself and other nearby components. So what we're going to do in this example is, given the resistance and the power rating of the resistor, what is the maximum voltage that we should apply across this resistor? So we're going to use this formula. P is equal to V squared over R. Now, because we're solving for V, we're going to rearrange the equation. I'm going to multiply both sides by R. So I get V squared is equal to the power times the resistor. Taking the square root of both sides, we get the formula to calculate the maximum voltage that should be applied across the resistor. So V is equal to the square root of P times R. So here we have a 1/2 watt resistor, and the resistance is 100 ohms. So half of 100 is 49. And the square root, it's 50. Whoa, half of 100 is not 49, it's 50. But you know what? It is easy to take the square root of 49. That's 7. So if you want to get a ballpark of your answer, you know it's close to 7. The square root of 50 is about 7.07 volts. So that is the maximum voltage that should be applied across this resistor if you don't want it to overheat. Now, the next thing that we need to talk about is how you can connect multiple resistors together. If you wish to increase the resistance in a circuit, you want to add resistors in series, because the total resistance of resistors connected in series is the sum of each individual resistor. So the more resistors that you add, the greater the total resistance will be. In a parallel circuit, the more resistors you add in parallel to each other, the total resistance actually goes down. To calculate the total resistance, you can use this formula. It's 1 over R1 plus 1 over R2 plus 1 over R3 raised to the -1. And I'm going to give you an example of that shortly. But right now, I want you to understand something. In a series circuit, there's only one path for the current to flow. And this is the only path that it can flow from A to B. In a parallel circuit, there's multiple paths for the current to flow. Going from A to B, the current can flow through R1, it can flow through R2, and it can flow through R3. And so that can help you to distinguish whether if two components are connected in series or in parallel. If there's only one path for the current to flow, it's connected in series. If there are multiple paths for the current to flow, it's connected in parallel. Now, there's some other important things to take into account here, because in a series circuit, the current flowing through each resistor is the same. So the current flowing through R1 is called I1. The current flowing through R2 is I2. Each of these currents, they're the same current. I1 is equal to I2, and that's equal to I3. Now, in a parallel circuit, the voltage across each resistor is the same. So the voltage across R1 is V1. The voltage across R2 is V2 because they're connected across the same 2 points. So that's another thing you need to be aware of when dealing with series circuits and parallel circuits. In a series circuit, the current flowing through each resistor is the same. In a parallel circuit, the voltage across each resistor is the same. Now, let's say we have two 10 ohm resistors. There's a lot of things we can do with that. With those two 10 ohm resistors, we can get 3 different resistor values. We could use one of the 2 resistors to get a resistance value of 10 ohms, or if we wish to increase the resistance, we can connect the 2 resistors in series. And so the total resistance across these 2 points, let's call it point A and B, is now R1 plus R2, so we get 20. Now, if we wish to decrease the resistance, we can connect the 2 resistors in parallel. Now, whenever you connect 2 resistors in parallel, if the 2 resistors have the same value, if they're identical, the total resistance of the 2 identical resistors will be half of their respective values. So it's going to be 5 ohms. So thus, if you want to increase the resistance, connect resistors in series. If you wish to decrease the resistance, connect them in parallel. Now, for those of you who want to see the calculation, it's going to be 1 over R1. R1 is 10 plus 1 over R2 raised to the minus 1. So 1 over 10 plus 1 over 10 is 2 over 10. And when you raise something to the minus 1 power, you basically need to flip the fraction. If you flip the fraction, the exponent will change sign. It will change from being negative 1 to positive 1. 10 over 2 to the first power is simply 10 over 2. And 10 divided by 2 is 5. And so anytime you connect 2 identical resistors in parallel, the total resistance will be half of their respective values. Now, the next type of device that we need to talk about is the light bulb. The light bulb converts electricity into light energy. And this particular light bulb does so through a process known as incandescence. In incandescence, what happens is when a metal gets very hot, it's going to become red hot first, and as it gets hotter, the color changes. It'll turn yellow, it may even be white hot. And so when a metal is very hot, it begins to emit not only heat energy, but light energy. And so incandescence is a process where you can generate light by heating up a material. In this light bulb, there is a tiny wire called a filament. So this is going to be green color. And the reason why it has to be so thin is because if you have a lot of electrons flowing through a very thin wire, it's going to be very easy to heat up that metal wire. And as the metal wire gets hot, it's going to emit light if it reaches a high enough temperature. And so that's incandescence. When you apply an electric current through a very tiny piece of metal, it can get hot to the point where it emits light. Now, with these types of light bulbs, they're not very efficient in generating light energy. They work, but a lot of the energy is wasted as heat energy. They generate a lot of heat. And there's another type of device that we could use that can also generate light energy. And this is known as an LED, a light emitting diode. Let's use a green LED. A light emitting diode also converts electricity to light energy, but it does so more efficiently. It doesn't use the process of incandescence. In fact, LEDs are monochromatic light sources. They generate light of one specific wavelength. And as a result, these devices are very efficient at converting electricity into light energy. Very little heat is generated. They don't use up that much current. A typical green LED has a voltage drop of 2 volts. And the amount of current that usually flows through an LED can vary between 0.1 milliamps to 20. If you put too much current in an LED, it can burn out. So there are limits. When you're buying an LED, you need to look at the manufacturer specifications in terms of what the maximum forward current should be. But this is typically the range of most LEDs that you'll encounter in electronics. Now let's say we have a 9-volt battery. And we want to determine the value of the current limiting resistor that we should use in order to get a current of 10 milliamps flowing through this LED. Because you don't want too much current to flow in it. So this is when it's useful to add a current limiting resistor. How can we determine the resistance value that we need? Well, for one thing, we need to determine the voltage across the resistor. The LED will use up 2 volts out of the 9 volts that the battery is providing to the circuit. So the resistor is going to take up the other 7 volts. And this is the basic idea behind Kirchhoff's voltage law. The sum of the voltage drops in a closed loop or in a closed circuit must add up to 0. The battery has, because it increases the energy to a circuit, we're going to put a positive voltage to it. The resistor and the LED, they absorb energy from the circuit, so we're going to put a negative value. If you add 9, -7, and -2, you'll get 0, which satisfies Kirchhoff's voltage law. Now, in order to calculate the resistance that we need, we could use Ohm's law. V is equal to IR. So solving for R, it's going to be the voltage divided by the current. So we have 7 volts across the resistor, and we want a current of 10 milliamps across it. By the way, if you divide volts by amps, you're going to get the resistance in ohms. If you divide volts by milliamps, you'll get the resistance in kilo ohms. So just be aware of that. So if we take 7 volts divided by 10 milliamps, this is going to give us 0.7 kilo ohms. Now 1 kilo ohm is 1,000 ohms. So 0.7 kilo ohms is 700 ohms. So we need a 700 ohm resistor in order to get a current of approximately 10 milliamps in a circuit. Now the next type of device that I want to talk about is something known as a potentiometer. Now you might be wondering, what is a potentiometer? A potentiometer is a variable resistor. It's a device where you can adjust the resistance of a circuit. And that's pretty useful because you could use that to control the voltage across an element, or you could use it to control the amount of current in a circuit. But let's talk about the potentiometer. So here is the electrical symbol of a potentiometer. You can draw it this way. You can draw it this way. It's a variable resistor. But let's use this version of it. I want you to understand how it works. So let's call this point A, point B, and point C. Now let's say this is a 100 kilo ohm potentiometer. If C is at the middle of A and B, the resistance between A and C will be 50K. The resistance between B and C will be 50K. But the resistance between A and B is always 100K, and that's important. So let's say we move up point C closer to A. And this is still a 100K resistor. So the 100K potentiometer will still have a resistance of 100 kilo ohms between point A and B. That's not going to change. What changes is the relative resistance between A and C and B and C. So now, if the resistance between A and C is 25K, the resistance between B and C will be 75 kilo ohms. The sum total will always be 100 kilo ohms. And so sometimes you don't need to use all 3 points of a potentiometer. You may only need to use 2 of the 3 points. And so if we only use A and C, we can adjust the resistance of A and C from 0 kilo ohms to 100 kilo ohms. Now there's many applications of potentiometers. We won't be able to cover all of them in this video, but let's talk about the basics of it. One useful application of the potentiometer is using it for brightness control. Let me draw a better circuit. Sometimes my drawing skills is not what it should be. So in this example, I'm only going to use 2 of the 3 parts of the potentiometer. So let's use a 9-volt battery. And we're going to use a green LED with a voltage drop of 2 volts. Let's call this R1 and R2. And let's say that R1 is a 10 kilo ohm potentiometer. Let's call this point A, B, and C. So between A and B, the resistance is always 10 kilo ohms. But between A and C, it can vary between 0 and 10 kilo ohms. Now, if R1 goes to 0 kilo ohms, that's dangerous for the LED, because without R2 there, we could have too much current flowing through the LED. So R2 it serves to protect the LED in the event that R1 is tuned to 0 kilo ohms. So the maximum current of a typical LED is 20 milliamps. To determine our R2 value, let's assume R1 goes to 0. So R2 is going to be the voltage, which if we take the difference between 9 and 2 volts, the maximum voltage across R2 will be 7 volts, divided by a maximum current of 20 milliamps. Now, if you want to convert from milliamps to amps, divide by 1,000. 1 amp is 1,000 milliamps. So 20 divided by 1,000, that's 0.02. So 20 milliamps is 0.02 amps. 7 divided by 0.02 is 350. So we want R2 to be 350 ohms. So if R1 is set to 0K, the most or the maximum amount of current that we're going to get in the circuit is 20 milliamps, which means the LED will be super bright. But now if R1 is tuned all the way to 10K, then the total resistance in the circuit will be 10K plus 350 ohms. So thus it will be 10.35 kilo ohms. Keep in mind 350 ohms is 0.35 kilo ohms. So the max current, which will be voltage divided by resistance, that's going to be, we're going to have 7 volts across these 2 resistors equivalently if this goes up to 10K. So the total voltage across the 2 resistors will be no more than 7 volts due to the 2 volt drop of the LED. And the total resistance is 10.35 kilo ohms. Now remember, if you divide volts by amps, you get the resistance in ohms. If you divide volts by kilo ohms, you're going to get the current in milliamps. 7 divided by 10.35 kilo ohms is going to give us a current of 0.676 milliamps. So with this potentiometer, the current in the circuit can vary between 0.68 milliamps and 20 milliamps. So when R1 is set to 0K, the current is going to be very high, which means the LED will be super bright. If we adjust R1 to 10K, the current flowing in the circuit will be very low, which means the LED will be very dim. So thus we could use a potentiometer for brightness control. The potentiometer can help us to adjust the resistance in a circuit, thereby adjusting the current flowing in the circuit, thus controlling the brightness of the LED. So that's one of the many applications of potentiometers in electronics. Now, before moving on to the next topic, I want to mention a few things. For those of you who want more information on potentiometers, LEDs, how to calculate the current in series and parallel circuits, and even other things that I'm going to talk about later in this video, I'm going to post some links in the description section below this video. So feel free to take a look at that if you want access to other videos regarding electronic circuits. In addition, I have a playlist on electronics that you could find at my website, www.video-tutor.net. So if you want to see a playlist with electronics topics, feel free to take a look at that. And for those of you who want to see what equipment I've used when building electronic circuits and other science and tech stuff, you can check out my Amazon store. It's amazon.com/shop/the organic chemistry tutor. So if you want to see what type of multimedia I've been using or what type of electronic components that I've experimented with, and if you want to test it out yourself, you could find it all at this link. So feel free to take a look at that when you get a chance. Now, the next thing that we're going to talk about is the voltage divider network used in resistors, because the potentiometer is very useful in this case. So let's say we have two resistors and both of them is 10 ohms. And let's say we have a 12 volt battery. The voltage across the 10 ohm resistor will be half of the 12 volt battery. And let me give you the formula associated with this type of circuit. Let's call this R1 and R2. And let's call the voltage of the battery V. And we're going to say the voltage across R2 is the output voltage. The output voltage is going to equal the input voltage times R2 divided by R1 plus R2. Now let's adjust this circuit. Now this circuit works by reducing the voltage through power dissipation. The energy provided by the battery, some of it is dissipated in the form of heat. And because we're losing energy, we can decrease the voltage. But now let's see how we can incorporate a potentiometer in this circuit. So this is one way in which you can do it. So let's say this is R2 and the potentiometer is R1. Let's say R2 is a 1 kilo ohm resistor and R1 is, let's say, let's make it a 10 kilo ohm resistor. And let's use a 12 volt battery. So what we're going to do is we're going to calculate the range of the voltage across R2. So R1 can vary between 0K and 10K. So let's calculate the output voltage when R1 is set to 0K. So we know the output voltage is going to be the input voltage, which is 12, times R2 over R1 plus R2. So when R1 is 0K, you can just eliminate R1 out of the equation. It's going to be R2 over R2, which cancels to 1. So the output voltage will be 12. So let's say V out is equal to 12 volts. Now what about if R1 is set to its maximum value? In this case, R2 is still 1K, R1 is 10K. So it's going to be 12 times 1K divided by 11K. So the minimum voltage of this circuit will be 1.09 volts when R1 is adjusted to its maximum value. So using this potentiometer, we can adjust the voltage across R2 from approximately 1 volt to 12 volts. So that's another application of potentiometers. Now the way we connected this potentiometer was different than what we did before. This time, instead of just using 2 of the 3 pins, we used all 3. So I want to talk about when you see a circuit when you see a potentiometer connected that way, I want you to understand what's happening here. So we have our 3 points, point A, point B, and point C. And let's use a 100 kilo ohm potentiometer. Let me adjust this. So let's say point C is closer to point A, such that this is 25K and this is 75K. So the resistance between B and C will be 75K if B and C are not connected to each other. But what happens if we make a connection between B and C? Well, let's say we have a 10 kilo ohm resistor. That's going to be the resistance between point A and point B. But if we were to connect a wire between point A and point B, what's going to happen? Well, when electrons enter this circuit, they don't want to flow through the resistor. They're going to flow through this conductor because there's less resistance. And so the wire bypasses the resistor. The resistance between A and B is now 0 ohms due to the wire that's connected across the resistor. So once we connect B and C, the resistance of B and C is wiped out. So the resistance between A and B is no longer going to be 100 kilo ohms, but 75 kilo ohms out of that 100 kilo ohms will be wiped out. So it's only going to be 25K. So the electrons, they will flow through 25 kilo ohms of resistance. After that, they're not going to flow through the other 75K. They're going to go through this conductor to get to point B. So when you connect it this way, just understand that the resistance will be whatever the resistance is between point A and C. That's going to be the resistance between A and B. Now, I want to go back to the LED, the light emitting diode. As mentioned before, an LED converts electricity into light energy efficiently without generating much heat. But there's a device that works in the opposite direction, and that is a solar cell. A solar cell converts light energy, typically from the sun, into electricity. And so a solar cell is a power source, more specifically a DC power source. It kind of works like a battery in the presence of light, generating electricity that can be used to power your circuits.